Hello everyone. What I'm going to be looking at in this video is the equations of motion and specifically how you would derive them using calculus. All I've done so far is I have written the relationships between the variables displacement, velocity and acceleration on the board. If you want to, you can pause the video and view through them. I'm going to jump straight to the derivations here. Okay, so equation 1, v equals v plus at. What you do for that is you take the expression for acceleration as the derivative of velocity with respect to time, rearrange it so it looks like this, integrate integrate both sides. Now, if you want to make this easier, you can introduce limits. So, you're going to want to make sure your limits agree with each other, otherwise you're going to get a bunch of rubbish in this. So if you integrate with respect to time between 0 and t, you know that 0 corresponds to the initial speed, and t, a final time, corresponds with a final speed, or final velocity I should say. If it's one-dimensional motion, it doesn't really matter. So that's where these limits are going to come from. So what happens is, you're integrating what is effectively 1 with respect to velocity, and that just gets you v, but you've got your lower limit u. So just check that in there. Those two look so alike, don't they? Is that better? I think it is. Marginally. And differentiate acceleration in respect to time, and you get at. And of course the lower limit is 0, so we subtract 0 from that. Not really going to make much of a difference in this case. And now just rearrange for v. That's not anything. You're not going to get a PhD thesis for deriving that. I don't think. I'm not expecting. I'm either. Sadly. Really, life is so simple. So to get s equals ut plus half at squared, you need to not differentiate. Integrate both sides of this with respect to time. Now you're only doing it with respect to time this time. So, in the process of doing that, again, I'm going to make things faster, not having to worry about annoying constant c's and saying, oh, because at initial time t equals 0, position is 0 at this instant. I'm just going to put in the limits 0 and t, and I think the SQA allow that. You might want to check that in the past paper marking schemes, just to be on the safe side. And what you get for this one, velocity, the integral of velocity with respect to time is displacement, s, and integrate this term here with respect to time, and that gets you ut. Integrate this, and it becomes half at squared. Not anything too crazy here. Now, if you want to get v squared equals u squared plus 2as, I'm going to underline that, otherwise this is going to get even messier. What you could do is rearrange t, and that would get you, I'm just going to try and do this in my head, v minus u over a. That looks horrible. And then take this expression and put it into t squared here and t here, and that is one way of doing it. I think there's a much cooler way that I want to show you. I mean, substituting in some rearranged value for t and plugging it into another equation is not anything new, but this is a much more interesting way to get that equation. I'm not quite sure they'd accept this in the syllabus. Okay, now watch this. Substitute acceleration for dv by dt. Now, in the right hand side, we're going to substitute velocity for dv by ds. So acceleration times velocity is acceleration times velocity. And now, if you this is going to sound really dodgy, but there are quite a few things we do in I see people doing calculus that kind of look dodgy. Until you chew it over a wee bit. I'm going to multiply both sides by dt, and what's going to happen is they're going to cancel. And you end up with v times dv, if I just rearrange that a little bit, times v times dv equals a times ds. There we go. And now I have to integrate everything again. Now, the initial speed occurs when the displacement is 0. The final speed occurs after a given quantity, after a given amount of acceleration, when the displacement is s. So final velocity occurs when displacement is s. And then what you get is, now you're integrating velocity with respect to velocity. So you get this, half velocity squared. And you have to do the same, but with the lower limit. Half u squared equals acceleration, integral acceleration with respect to distance is just going to be as. Now multiply everything by 2, and v squared minus u squared equals 2as, and therefore v squared equals u squared plus 2as. Boom! That's another way to get that equation. However, I would be careful about actually using that method of derivation in the exam if you're asked to do that. I think what they are asking you to do, or what they're expecting, the examiners mean, is for you to actually take this expression for t out of the first equation and plug it into the second equation. Of course, both methods are equally mathematically correct, unless, of course, someone tells me, oh, but you multiply by dt back here. You can't do that. It doesn't work like that. They're not ratios. Except you treat them like ratios for differential equations when you separate the variables. So, don't know why that answer would be I'm not quite sure why this method would be any more invalid than solving differential equations by that method. Well, anyway, that's linear kinematics. That's the equations of motion derived by calculus. At least a slightly more fun way of doing it. And I guess I'll see you next time for rotational kinematics in the next video. And thank you for putting up with my rambling up till now. Bye for now.